Okay, thank you for the invitation. Good afternoon, good morning. I will start the presentation here. Today, we're going to focus on the second part of the presentation, what I call Program 2. It's basically some advanced concept regarding the Pore scale studies. Then we're going to move on to some topics regarding the core scale, as I call a new frontier, it's still in development. And then we have some case studies to discuss, and you can interact with me anytime, okay? You can interrupt me and ask questions or discuss some topics. And just before we start, I would like to do a briefing safe moment again. Today we're going to cover just how we can encourage each other during this pandemic time. I took this information from the World Health Organization. It's really important to be supported to the loved ones, to our friends and people around us. So please, those people affected, encourage them to keep active and to do what they enjoy to do. Share some important information with a reliable source of information, okay? And try to provide some common and correct advice for children, especially in this difficult moments. Interested in more information about these COVID-19 issues, please go ahead to this link and go and see some information, reliable information, okay? Then I would like to start. Today I will cover what I call the basic and advanced concepts regarding mainly multi-phase flow, or at least two-phase flow, what I look to show you. Just before we start, I'd like to show, just a moment please, show this video here. When you see this video, actually what I want to show you here is a two-phase flow simulation, in a Pnm-Based Numerical Simulation, covering, for example, two fluids inside a Pore system. This one here is a regular one, and you can see that we have filled with the red, what I call a red one here, and now you are invading with the blue fluid. But what's the idea here? I would like to discuss that in digital rock technology, you can perform what we call a routine core analysis. For example, yesterday we discussed about permeability and porosity and some other measurements as well, or some other numerical analysis that we can provide for example, formation factor or elastic properties. But today I want to talk a little bit about two-phase flow, especially. And what we need here in this step, we have to provide some information, important information about rock fluid and fluid interactions. This information is really important when we think about the simulation, what I'm showing here for you, because we have to provide certain boundary conditions, some real fits information when we are coding or we are evaluating a methodology here. So we have to be careful about what we are studying, we are developing, and we are testing. So that's why I will start our discussion here today, especially for this part of the special core analysis, focusing on this kind of rock fluid and fluid interactions, okay? It's a really quick overview. Probably a lot of people here, it's well known about these topics, but it's important because later we'll discuss in a digital walkway, okay? So I will start with the two really important concepts here, wettability and contact angle. So in the first image here, let me just put the pointer here. First image here, I'm showing you two different systems. One of them here, you have this kind of boundary, and you have in the middle like an oil drop, oil bubble. And the other one, you have this kind of water here and some kind of layer here around your boundary. And this is two different scenarios. The first one here we call like a water-wet scenario. You have the wet or water here around your let's say boundary surface, and in the middle you have the oil, like a separate phase. In the opposite way, we have what we call an oil-wet scenario. So we have oil here as a thin layer, and then in the middle, you have this kind of drop of water.
Excuse me, doctor.
Yes?
But your voice is not very clear. It's go up and down. Can you please adjust your microphone so it can be suitable for us to hear?
Okay. It's better now?
Yeah, yes, now it's better.
Okay. I'll try to keep the mic in this state. Okay. If you have any
Yeah,
problem, please let me know. Okay.
now it's clear. All right, thanks.
Thank you. And as I was mentioning, you have kind of two different scenarios here. And the water wet, when you have the same layer of water, and now oil wet, you have this kind of layer of oil. So it's important because when we start our simulations or our approach, our digital rock approach, we have to be careful about what we are specifying in our conditions. That's why I would like to start this with you discussing. And also, for example, if you have this kind of different scenarios, you have to fulfill your code, for example, with information about the contact angle. Yeah, it will be really important. And here I will just show you some simple images in a scenario when you have the water here spread across the solid face here, as you can see. It's a water wet scenario. You can measure this contact angle here, as I can show you here in this pointer. In the other scenario here, you have this kind of like here, and then here you have your solid. Yeah? So in this case here, I'm measuring this here because it's not a water wet condition. Yeah? It's like if you have oil here around your water, you have like an oil wet scenario. If you're invading your system. So just to give you a quick overview of these two important concepts, but I will move forward to just to give you the other important topic, what we call the interfacial tension.
Sorry, Dr.
Yes?
Goody, but how can we identify if the rocks is other water weight or oil weight? How can we recognize this?
Yeah, there are some possibilities. Yeah, the first one, for example, if you're talking about a digital rock way, we can change the wettability according to our understanding. Yeah? But for example, if you have a raw rock, let's say, and you have a system where you are trying to understand what the wettability there, you can perform like an averaging in your sample. Okay, it's a possibility in the lab experiments. There are some kind of measurements I will show you later, and then you can try to understand or identify the angles now between the surface and the fluid that you are interacting with the solid. Okay, I will try to show you later. There's an equipment that you can use here. I use this during my thesis, and you can try to identify the wettability there. You can try to measure the contact angle. Both information can give you some hints or some information about the wettability of the system. Okay.
Okay.
And for example, this part here, I'll just mention interfacial tension. It's an important concept as well, because it's related to the interaction of fluid-fluid interaction. In this case, we are just considering oil and water as the phase here. Yeah? We have the surface. You can infer this information of the interfacial tension in a simple calculation here. When you have this measure of the contact angle and you have this stress here, and then you have this kind of relation between them, and then it's like a measurement of the interfacial tension. Here's just a 2D overview, a really simple concept here, and then you can see 3D reconstruction, or at least a 2D scheme of the same concept. But just to give you a brief view, that's really important concepts that we're addressing here regarding two-phase flow, at least for multi-phase flow, of course, but at least for two-phase flow. So contact angle in the first part, yeah? And then you can correlate contact angle with the interfacial tension. And following the question that you previously asked me, there is some kind of equipment and some kind of procedures that you can perform to try to understand the wettability of your system. And I'm showing here in this image, it's a goniometer. It's the name of this one is it's a dropship analyzer. It's from CRUS. It's equipment that you can measure all the interfacial tension and also the contact angle. Actually, you can perform different procedures to get this measurement done. Okay, and I would like to show here that based on these values of angle, you can have some idea of the wettability of your system. So I just picked up this information here from this. I really encourage you to take a look at this here. Really important for the regarding the wettability and the content angle measurements. In this case, he just introduced the idea of some range, some value ranges here that you can probably find the wettability of your system. For example, if you're considering
excuse me, Dr. Goddy, but the problem voice is happening again. Can you adjust your microphone?
Can you hear me better, Raul?
No, yes,
Yeah.
okay.
Mm-hmm.
Can you keep at that position? Just keep at that position, your microphone.
Okay. I'm keeping this position.
Yeah, that's good.
Sometimes it's just a connection problem. Okay, please let me know. Thank you. Mm-hmm. Regarding the water wet scenario, for example, we're considering as a minimum contact angle here 0 degrees, and then we are move on for a neutral wetting, what we call a mixed wettability between 60 and 75 degrees minimum contact angle. And then for a oil wet scenario, we are dealing with higher values of angle, let's say between 105 and 120 degrees. This is the minimum contact angle scenarios for these scenarios here, or from water wet to oil wet scenarios. And we have also the maximum contact angle that Anderson mentioned. If you think about the water wet scenario, between 60 and 75, for a neutral or mix between 105 to 120, and then if for oil wet, a maximum contact angle of 180. This is a really interesting table because it gives you some ideas what you can find in your system regarding the measurements that can be provided by this equipment. It's a really important topic. It's a field of investigation. Okay, there are several theses and papers regarding this part here. A lot of them experimental ones, try to identify or try to understand, or at least creating developing new methodologies to get a reliable measurement. Okay, and then with this equipment, we can take a look at the drop at the bubble here, as I mentioned. So based on this equipment, you can do this kind of measurements. There are different approaches. I've just put this one here as an example, using that equipment from the previous slides. And then every 30 seconds, you do this kind of measurements in a timeline of 24 hours, just to get the measurements from this angle here. And there's a correlation between them when you use this equipment. I just use this equation here to give you a quick overview as well, because it's the dependence of the radius of the curvature that you are finding there, the difference between the density of the two phases, for example, of the oil and brine, for example, if you are this system that you are evaluating, you have to consider the gravity as well, and also the interfacial tension that's here, this last parameter. So there's a correlation between them. Of course, there are other post-processing, other different equations that you have to solve, okay, in order to get a reliable, or at least a correlation with the data, the lab data that you have, okay.
Sorry, Doctor.
Yes.
But what does the B capital refers to?
Which one, please?
The B capital.
No, just a parameter. It's a parameter that you use later in a different equation to calculate. It's a parameter that you have to calculate, and then you have to fulfill in a different equation to have an idea how much your bubble is spreading there. Okay, I just put this in a simple way. Okay, I will not go too much in this information, because, as I mentioned yesterday, you have a lot of different information, a lot of different techniques. Each different technique has some limitation. It's important to keep in mind that digital rock, you are thinking in a way that you can do everything in a numerical way. But at least you have to think that some of the lab experiments give you some information data, or give you some important hints in order to keep your simulation or your numerical analysis as close as possible to the real world. Because as I said, and you are modeling. Yeah? In every model, you have some limitations, but you also have some limitation related to the lab experiments, to each different technique that you can use to enhance your results, to get a better result. So it's just an idea. I can give you later the more information. A lot of friends, some physics here at the university regarding this kind of acquisition. Okay, you have to perform several steps in order to get a reliable data. But it's just to mention that you can measure this. Okay, it's important to keep in mind. You can measure this in the lab. You can use this kind of information during your digital rock evaluation, or at least if you try to correlate the real measurements with some numerical analysis, numerical experiments, then you can do this kind of quality control if you are using the same parameters in the same conditions, okay? So you have to keep in mind that the boundary conditions, they are really important for both worlds, for lab and also for the numerical activity, numerical analysis, okay? So moving on again, I will just try to talk a little bit about the capillary pressure, because we are going to talk about this during the presentation when we generate the PC curves and then move forward to other analysis. So I try to keep it simple, put this kind of scheme here that you can see that's oil and water and this capillary here, and then between them you can identify these meniscus, and then based on this equation here, that's a really simple equation in this case. You are correlating the capillary pressure, the first one here. You're correlating interfacial tension that we mentioned before. You're correlating contact angle between the phase, effective radius, this part here, effective radius between the two interfaces. This equation here can be used, for example, during a simple two-phase flow simulations as your parameter to control the difference between the pressure difference between two different phases, okay? It's a really well-known equation. It's used, for example, during Pnm-Based Simulation. You can correlate the pressure differential between these two phases with this PC equation here, the simple one. I'll also try to put in a scheme regarding a rock and this kind of fluid film here, in this case a water film, and this one here is around your system. That's the second phase, let's say in oil, and then you can correlate again the PC based on the interfacial tension and this radius between this phase here, the outside, and then with the meniscus. So really simple equation, just to keep you aware that we are dealing right now with the capillary pressure, the difference between two different phases, because we're trying to understand, or at least try to simulate as best as possible the interaction between the two fluids in a pore system that can provide you later some graphs, for example, for PC curves, some KR curves, and all of them are related with the differential, the pressure differential here that we are discussing. Okay, so just to keep in mind that I'm just putting here simple equations, simple ideas. Probably a lot of people here just heard about that, but because we are moving forward to identify what we can do with the digital rock technology. Okay, so as mentioned, yes.
Sorry, Dr. William, I just want to ask, during the field job, the core analysis taking, this is interfacial tension is actually properties of the rock, that's right? And also is properties of the fluids. So during the field operation, we are just sending the core to the lab. But what about the fluid, like the oil density, water density, the other things that should be also measured? But
yes. Of course, when we are dealing with this kind of simulation, you have to be aware about the density, viscosity, contact angle, a lot of different information.
I mean, during the lab calculation and measure, they also take in their consideration the reservoir fluid itself, like the oil inside the reservoir, the water salinity, for example. And if we like, for example, we have high salinity water, and then we start injecting fresh water, for example, this will affect the interfacial tension of the rocks, and the waterability will be changed, or
Reservoir.
this will not be changed.
You're thinking, for example, if you have a brine of higher saturation, for example, a high salinity, and then we are trying to insert some water, fresh water, let's say, and if you're changing the density and some properties there, yeah?
Yeah.
Now, in this case, you have to we have to be aware that you are changing the fluid properties there. As you mentioned, you are trying to change the density. Somehow you can, for example, changing, I don't know, for example, viscosity and the interaction between them. Of course, you have to be careful about it. If you are changing these parameters, of course, you are changing the interaction between them. And if you are thinking about simulations, for sure you are changing as well. But as I mentioned, you can start with some lab measurements to have an idea what's going on there, and then you can try to model it in a numerical way, in numerical analysis. But yes, for example, here I'm just talking some basic concepts here, because we are moving forward to the digital rock. But you can perform several different measurements in the lab. For example, if you're performing a coral flooding experiment, for example, you can use a brine with, let's say, a carbonated water there. You can use different density, brine densities there. It's a different world as well. You can try, you can see what is going on there. For sure, you change the parameters, but what you're going to change in the end of your experiment, for example, then you have to be careful. You have to control each one of the simple parameters to get an overview of the results. Here, as I mentioned, it's just a quick overview. You probably know about it, but just to move forward to the what we can do with the digital rock technology. Okay.
Thank you.
And then, based on this, the capillary pressure, and then move on to the water saturation, I would like just to put here again some of the concepts, really simple, about the water saturation. And as I defined it here, if you have a system here, you can define this water saturation, the volume of water, and the total regarding the total volume of fluids that you have in your own system. So it's important because all of our graphs that I'm going to show you later is based on the water saturation. For example, this graph here on the right is a capillary pressure versus water saturation, or at least the wetting phase saturation. Let's say that we are working on a water wet scenario, and we are performing, for example, a drainage. So in this case, it's really important here what I'm going to mention. Because there's sometimes some misunderstanding between these concepts. During the extraction of one phase in the porous medium, you're displacing one phase by the other. So we have to consider that there is a wetting in a non-wetting phase. And by definition, you can take a different reference. I can use, for example, Professor Blunt's reference in the book Multi-Phase Flow, because there you can find a really good description. I will show you later, but just to mention that is the drainage here, you are displacing the wet phase with the non-wetting phase. Let's say that you have a water wet scenario, and you are injecting oil to displace the wetting phase, that's water. So we're considering this a drainage, okay? And the emission will be the second step when we are displacing the non-wetting phase phase. And so let's keep simple as this. You have, for example, on a water wet scenario, and you are injecting oil and displacing the wetting phase, that's water. So we have like a drainage. If you do the opposite way, in the complementary way, you have this wetting phase being injecting and displacing the non-wetting phase, you have this inhibition. So here, just to show you, the first curve here is the drainage process, and this one here is the inhibition process. And then you have this kind of, show you in this next slide here. It's all, when you are dealing with this kind of water wet scenario that I mentioned before, you can reach this value here. That's the minimum, is the irreducible water saturation. Even if you increase your pressure, you will not go further into the pores, okay, the pore system. So it's important to keep in mind that you can reach this saturation, but when you do the opposite way and you try to, you are displacing the wetting phase, the non-wetting phase with the wetting phase during the inhibition, you can reach a value, what we call ACOR, saturation. And as you can see here, you never reach the same value now. So it's characterized in a hysteresis, okay? So it's important because you're gonna work with digital rock evaluation, depending on the sample that you're selecting, depending on the volumes or the size of your sample, you can reach different values for a saturation. Somehow you have to not only correlate, but you have to be aware that it's an important value that you can infer during your simulations. Yeah? You can find this from your own numerical analysis. You can try to do light quality control based on some experiments. That's why I'm trying to show you these concepts here, because some of this information that came from the lab can help you a lot. Some of them will not be available sometimes when you are performing the numerical analysis, but then you can have some ideas, yeah, based on the definition of the right equations, and based on this kind of pattern that you're gonna find performing drainage or imbibition simulations, okay? So in the next slide, I would like to show, I just copy here from the professor's the drainage process, yeah? Because it's really important when you think about the relative permeability or the PC curves, for example. We have to be aware and not misunderstand some of the ideas. So I'm just simple as he wrote in his book. Yeah? Started the phase with the wetting phase, and we are going to allow the non-wetting phase to enter, what we call the primary drainage process. Yeah? So as he mentioned, it's the first time that we're going to do this, so that's why it's the first. It's a primary drainage, and then we can start with the saturation of one. As I mentioned, saturation, it's not like a fraction. Yeah, in this case here, just giving an overview, it's between 0 and 100 for the water saturation, and the other one is between 0 and 100. But just to give a really quick overview of this, because sometimes in the industry, when you read some different material, you have different concepts about drainage, for example. And I'm keep it simple as Professor Blunt defined, okay? I think it's a really good definition. You're gonna use this for the entire presentation for the digital rock analysis later, but it's a really simple idea. And when we're gonna perform the imbibition process that I'm gonna talk later, we're gonna do this in the opposite way, okay? We're gonna displace the non-wetting phase with the wetting phase. So, just to keep it simple, to give you the ideas for you, and then I will start to talk a little bit about what can we do with this digital rock approach. Yeah?
Sorry, Dr. William.
Yes.
Sorry. I I want to ask you about this PC curve, which appear in the previous.
This one.
Yes, this one. So this is drainage and imbibition. So
yes.
So for drainage, like we are going to simulate what originally happened in the reservoir before, like when oil immigrated from the source rock toward the reservoir. That's right.
In this case here, we are, let's say you have your system completely filled with the phase. Yeah. So we have to reach what we call the saturation. So that's why we have performed this experiment here. You can perform this experiment in a numerical way as well, because you have to reach this value here. Even if you are increasing your capillary pressure, you cannot remove this wetting phase here that you are dropping in these small pores, and due to these high capillary values. And if you are increasing, you cannot remove this. It's important when we are performing this, even in experimental or medical experiments, You have to get the result here. It's a really important one. Yeah. If you perform the opposite way, yeah, we are going on an inhibition process, then you can get the value of the residual oil saturation, and we have to perform this as well. Yeah. If you are checking how much oil we are letting there. Yeah. So I don't just show you in a simple scheme here the two processes which are related to this the displacement and the relation between wetting and non-wetting phase. Okay.
Okay. So in this case, this can give us like for an idea that even with the very good injection rate and very good injection project, even though we will lose some oil behind us, right? If from this graph, or it is not related to that.
Well, it's just a scheme. Yeah. For example, as I mentioned, let's say that you are trying to perform this kind of centrifuge method when we are generating the PC curves. Yeah, you have to saturate your sample. Yeah, let's say with brine, and there is a minimum value that you have to consider as a well-known saturated media. Yeah, and then you're going to perform, for example, injection of oil control. In your system. Yeah? You're displacing the wetting phase. Let's say that's a water wet scenario. You're displacing the wetting phase with the oil that's in the non-wetting phase. And by the end, you reach this value here. Of course, depends on your pore system, depends on the several other relations that you have to be careful about related to the pore scale interaction. Yeah, that's why I started here the presentation, mentioned the pore scale study, because as I'm gonna see later in some case studies, we can perform this kind of evaluation in a digital rock way, focusing on the pore scale perspective. And it's really interesting because you're focused on the right fits for your problem. Yeah, and if you have this kind of interaction, how can we solve that? How can we model? How can we at least evaluate the results? So you have to be careful about it. You have to be aware that in the experiments you're gonna find some limitations as well. But of course, you're performing this kind of procedures here. You're gonna find this reducible water saturation. Depends on your sample. Depends on some other parameters related to your sample as well. But yes, it's a pattern that you're gonna find. Okay.
Okay. Thank you, Doctor. Thank you.
And just regarding the two-phase modeling, as I was mentioning, yeah, you have to consider all the previous parameters, all the previous concepts that we discussed here, because as I mentioned yesterday, we have different methodologies to perform the numerical simulation. And again, there are three main ideas here. I try to put some results here related to let's bottom simulation here. Okay. You can see, for example, in this scenario here, you have a phase here, this phase, you have a wet phase here, and a wet phase here in a primary 20, for example. And this one is using let's bottom method. As I previously mentioned, you are trying to correlate this with with mass particles and the interaction between them. Yeah, so we will have to correlate this with the Navier-Stokes equations to get a better overview. As I mentioned yesterday, it wasn't in compressible media at that time. You have the final volume method with fluid dynamics based on generation of mesh. And you see here some other experiments related to two-phase flow as well. I really encourage you to take a look carefully at these references here, okay? Because you're going to see a lot of material there, a lot of results, more ideas related to the modeling itself, or to how to solve the problem. Okay, one here is a Pnm-based solution. So as you can see, it's the same model that I previously showed to you. It's related to a simple cube. You are displacing the water wet, the wetting phase, no wetting phase as well. And I really encourage you to take a look at these scenarios here. I'm going to show you just a quick overview of one of these. This is the Pnm-based simulation here. The next slide. Just to show you how you can try to understand this difficult concept in a simple way. Of course, as long as you are understanding your problem, you are moving for different techniques, you can improve this or that, but at least you have to be aware of what you need in all the parameters that you have to solve. Yeah? In this case here, I did a Pnm-Based Simulation. Okay, it's a static modeling. In this case, force dominating the system, and as you can see here, we are relating this to the kind of pressure that we previously discussed. You can see this equation here, the same equation we described earlier, because in this case, in Pnm, we're describing the pore body and the pore throat, and the connection between them. For example, in this image here is a really good scheme from Professor's Mirov paper. So you can see that you can connect pore bodies with a pore throat here. You can change the geometry of the pore throat, for example. Okay, it is a simplification. Of course, it's a Pnm-based simulation. We just give an overview, the aspects, or at least what you have to understand in the problem to solve the two-phase flow there. Yeah? In this case here, we are working with a triangle here. You can see there's some corners here. And also the pore bodies is a different shape. It's not a spherical shape. Yeah? It's like a cuboid or a cube that you have this kind of corner angles as well. And there's an interface here, as you can see, yeah? Between two different fluids. This is one of the possible approach. There's a lot of material that was already published and have been published. For example, there's a paper from this year from Dr. Bultrace from the Kent University regarding the distribution process using Pnm approach. Really interesting because it simulates some of the phenomena that it was not modeled before. Yeah? So it's really interesting. I can send you later if you are interested. But this is one of the possible approaches, okay? And then if you can correlate all of these equations and you can perform the numerical analysis, you can see this kind of results here. Just a moment, please. You can see kind of course, it's a really quick simulation here because I improved I took like a time frame, a really simple time frame. But it's a possible phase flow simulation using a Pnm approach. You can perform these using different methods, as I mentioned before, using Letts, Boltzmann, using CFD analysis, for example, finite element analysis as well. Each one of them has these pros and cons, for example. Here you are a simplification. When you're solving Letts, Boltzmann methods, you are dealing with different equations you have to solve and the interaction between the particles there. Of course, depends on the technique, depends on your resources, for example, computational resource that you have. It's really important that you have to keep in mind that sometimes you are performing some lab experiments that take some time, a long time, for example. But if you are performing this kind of numerical analysis, you also have to perform using a good hardware and a robust hardware, because sometimes you have to do this kind of parallelization computation to improve, to speed up your computation. Yeah? This one here, it took me some days to perform, but I was trying to check. This is on a complete sample. Yeah, it's a plug. I reconstructed all the pore system there using 9 micron pixel size, as I mentioned yesterday. I was trying to capture the peak of distribution of the pore radius there, and using this 10 micron voxel size, I could reach this value. And this one was a good experiment. I could correlate this with experiments in centrifuge, and as we discussed yesterday, a lot of results you can compare with the lab. And of course, we have some limitations in the computational modeling, but we also have some limitations when you think about the lab experiments as well. So correlating them, it's okay, it's good. Yeah, of course you have to try to do this kind of quality control, but be aware that you have limitations in both worlds. Okay. This example here is one of these tests that we can perform in the lab. Yeah. There are some experts here that I saw through this morning. from Brazil that you work a lot of these experiments here. When you perform the centrifuge method, you are trying to generate the PC curves. Yeah? Let's say that we are in the same example that we started we discussed it previously. We have this kind of water-wet rock. Yeah, we have the rock filled with brine, and then we try to perform this primary drainage, injecting oil to displace the brine. Yeah, so you can perform this using the equipment, a centrifuge. There are some equations relating the capillary pressure with radius in the angular velocity, and some correlations with the volume of fluids that you have. I'm not discussing details of the equation, even an overview that you have some results from the lab. You have to do like a post-processing analysis of your results, okay, of your lab results. And you can try to correlate with your numerical approach that you are trying to solve the previous equation I show you for PC, for example, related to PC SW curves. Here, just to compare, one is the plug from the centrifuge in the red curve, and the other is a different, is a digital rock simulation. It's a numerical simulation based on digital rock approach, and you can see that's reaching the same water saturation. Of course, in this one here, they try to compare the plug with a larger sample. Yeah, just a correlation between them, because in this numerical approach here, from this, I'm going to show you some of the results later. But he was trying to compare some results for the larger core, yeah, but a larger sample. But in this case here, as I mentioned, limitations. Some limitations from the lab approach. You have to perform you have to solve some equations. You have to consider some scenarios. But we're going to do this also with numerical analysis. In this case, based on some information that you have from the rock, from the lab as well, or even if you try to do like a sensitive analysis, yeah, you can perform the simulations. The numerical analysis is on a probable scenario that you're going to find, for example, in the reservoir. So it's a possible way to do this evaluation. Yeah? And here, just to show you some other results based on the numerical approach that you have. For example, this one here, you have the MICP PC curve, yeah, in black, as you can see here, and you have this phase 1 and phase 2 related to digital rock analysis. One of them, the first one, related to analysis with a subsample with a predefined voxel size. Okay. When you do the acquisition of the core, we have to specify this. I mentioned, we discussed it yesterday. You can move forward for a subsample to get the higher capillary pressures, yeah, and then you can correlate them, and you can check it. You can do this kind of cross-check with the lab experiments, see if you have like a good result or not to move forward. Yeah? That's one of the things that you can use to do quality control steps during your workflow and the digital rock workflow. Yesterday we saw this. Yeah, some steps we have to stop there. We have to take a look to analyze to see the results are okay or not. You have to perform this quality control using, for example, MICP, Pore information, and then you can go to the other step. Yeah, but even though you can define a workflow, you have to be careful about the limitations of each step. We just discussed about it, but it's really positive. Then, okay, of course, you can generate key curves as well based on digital rock analysis. And here's just a comparison between the lab and the digital rock. So you can perform this kind of evaluation from your sample, yeah, regarding the different scales. For example, you can work with the whole plug, some simple subsamples that you can select from a larger sample. You can perform this kind of evaluation scale approach. Okay. We're going to see this when we talk a little bit about the upscaling procedures and how we can go, we can move forward in the direction of core analysis. Okay. Here again, just to a quick overview, you saw yesterday, but MICP, as I mentioned, you have this kind of distribution of pore throat radius distribution. You can correlate it the numerical analysis that you can perform using digital rock technique. Okay, here again, yeah, in red you can see that you can find the distribution using a specified voxel size, acquisition and micro CT equipment, and then in the second part, performing with a high resolution in a different region. Here, for example, you can see the region with larger pores and the one with smaller pores. And you can perform both of them and try to correlate with the MICP. Okay? And if it's okay, this kind of correlation here, this kind of selection of the subsample, it was okay. We can move forward to perform other kind of experiments, numerical experiments. Okay, it's a quick overview again what we discussed yesterday about the MICP, because MICP it's experiment when you are performing this kind of two-phase flow tests, but based on mercury and, for example, air. Yeah, I'm not talking about oil and water in this case here, but you can correlate both of them. Just to explain a little bit with the equations. And then for this case here, for the PCKR curve, for example, and digital analysis, I selected this study here from a carbonate reservoir in Middle East, and using digital rock approach. Yeah? And as the main bullet here, I pointed that digital rock could be compared with SCAL results, yeah? Measurements performed before. It was a program that they could scan. I'm going to show you in the next case studies how we can do this for the whole core in the interaction with the plugs and the smaller samples. Okay. Once you can perform the scanning in a larger volume, you can perform the selection of the plug, and inside the plug you can select the region to perform higher resolution analysis in order to be possible to simulate using let's both method some two-phase flow analysis. Okay, so two-phase flow simulations. I put here some highlights here that to generate the PC curves in let's both method. Okay, as I mentioned in this case, as a sample, and you can perform this in several scales. In this part here, I'll not address this. I will address this later related to the scaling procedure, but to give you an overview that it's possible to generate the PC curves based on the subsample if you pass all the quality control steps that I mentioned before, and you also can correlate these with larger volumes. Depends on, of course, the resolution of the acquisition that you performed. Okay, this case here just to show you some correlations of lab experiments, numerical ones here. Numerical is this circle, orange circles here, yeah, and the others are the result from the centrifuge. All of them try to reach the same value of water saturation. In this case, even with digital rock analysis, it's possible to perform this. Okay, in this one here, they selected 4 different whole cores and try to put them in this way to create like a composite, a different structure. And they performed some evaluations on this scenario. Yeah? But what I would like to highlight here in this paper, of course, I will send you later this reference. You can take a look at the paper itself. But what I would like to enforce here, it's the idea that you can work with different scenarios. Yeah? In this case here, for example, in the second region here of the section that they are evaluating, they try to understand the kind of adaptability in the system. As you can see, they performed some numerical analysis here. This scenario 1 here, it's you had the similar adaptability conditions to the other whole course, next to a oil wet scenario 1 here, and the other is more like a water or a water wet scenario. Okay, and there you could see this kind of results. Yeah? You can analyze, correlate scenarios based on the changing of your adaptability. This kind of sensitivity analysis that can be performed using digital rock approach, you can save a lot of time performing this because it's a numerical exercise. Yeah? You're changing parameters in during your numerical evaluation, and then you can see the kind of results that you have. And of course, you have to be aware if it makes sense or not. You know? If it's a real situation, or for example, you can do this different scenarios, real scenarios, because you try to understand if this kind of changing notability could match with the real data that they got from the lab. Yeah? This is one of the advanced, one of the real gains that you have from the digital rock perspective. You are saving a lot of time performing this kind of simulations here. Sometimes it's not possible to perform this in the lab. Let's say you have a sample, you try to perform two different scenarios, but one of them you're changing your own sample, the Pore system itself. So you're not dealing with the same structures. But here, when you do the acquisition and you have the 3D reconstructed sample, you have the same Pore system, yeah? The same boundaries, the same conditions. So you can perform this kind of evaluation, just changing some of the parameters during your computations. What I think is really, really great, yeah? When you think about the time and what you can do when you are not changing your real rock, you are not trying to cut or to try to come back to the real watability scenario, for example, in a real rock. Yeah? And then just to move forward, I call this part here the new frontier, yeah, when you call about the core scale. Nowadays, there are several studies regarding the different upscaling procedures. I'll try to address some of the ideas that Ingrain can use, okay, during these workflows. There are some already published material that I will show you here. And one of the ideas is that if you have the cores here, you have to understand happening in the micro scale. Yeah, as I showed you before, you have this kind of thin layers around the pore boundary that is related to two-phase flow. You have to understand the physics behind it in order to try to recognize the same pattern in a larger volume and then try to correlate to the whole core that you are investigating. And that's one of the challenges, yeah, nowadays. I put three main topics here that I think can do like a short review of the upscaling procedures. One of them is that you can perform this kind of multi-scale, multi-resolution acquisition. For example, you can perform this acquisition here for the whole core, as you can see. Yeah, it's a reconstruction. This core here, we can perform the acquisition using a CT scanning, not exactly a micro CT, but with a low resolution, okay? And then you can select some regions to perform the high resolution acquisition and apply, for example, and then you can correlate this with an even higher resolution in a micro sample to understand what is going there, and then try to correlate this information in the other and come back again to the larger volume. Why, in the second option here, we have some kind of trends related to some of our parameters. For example, trying to correlate permeability and porosity in some samples, try to correlate formation factor in other samples. For example, this is a possible approach as well. It's useful, I'm going to show you. And then one of the ideas is that we can perform this kind of downscaling to understand what's going in there in order to perform scaling again. So that's why I put this here. Yeah? You can see it's like a complete workflow that you have to fulfill to understand the many issues regarding the upscaling procedures. Yeah? I'm going to show you some ideas behind these possible procedures here. One of them, I will start with the idea of what we can get about information in the multi-scale, multi-resolution approach. Then I'm going to show you some case studies that they are considering the trends and this kind of evaluation of the whole core until a micro sample, yeah, a subsample that we selected from the previous plug. And then I will finish with this kind of correlation between downscale and upscale. The first idea here, when you talk about multi-scale, is that sometimes we're just losing some information, as we discussed yesterday. depends on the voxel size, the resolution that you are working at. So here, I'm just show you an idea of the, if you have, for example, an image, yeah, a model, and you perform the acquisition of find voxel size, you can recreate, you can reconstruct the Pore system. Let's say the red and white polars and Pore floats here. It's a work from Bootface. It's really great. I encourage you to take a look at this as well. But then there are some regions you can understand what's going on there. It's an unresolved region. So one of the approaches that you can do, that's one of the possibilities, is to do the higher acquisition, selecting these regions here to understand. Yeah, there are some other techniques that you can perform together to get a better overview. Okay, so let's say that you are doing this with a 10 micron voxel size acquisition, then you can move, say, 5 micron voxel size acquisition. So we are increasing your resolution. You are identifying more Pore system in a resolved region that was not captured before. But then there are some numerical or at least some modeling approach that can be possible just using digital rock approach. One of them I took from the risk, the reconstruction of this micro Pore systems, how they are changing the permeability of the system. So it's just a possibility using digital rock. It's like an R&D analysis here. Is just to give an overview that we can perform several acquisitions in several scales. Okay, it's a really important point. Just to give you an overview of this, here, if you have a well-defined Pore, let's say this here, and you have this resolved region, it's a darker gray, but in this resolution you didn't capture the Pore system, you can perform this kind of numerical or modeling analysis there, or you can perform this kind of high resolution analysis and try to correlate them. What I'm trying to show here is that you can infer some information of these unresolved regions, you perform the higher resolution and try to capture the behavior and propagate this behavior and the original image. Okay, so it's like a multi-scale, multi-resolution approach. You can perform this to introduce some sub-resolution porosity in your system. You are losing it when you perform some using a specified voxel size, but you can search this value if you are increasing your resolution, you are enhancing your image. Okay, so it's a possible approach in your scale and populate some information in the unresolved regions here in gray, based on the high resolution results that you can perform. Okay, it's a possible approach to do this kind of upscaling, downscaling, upscaling in a small volume. Okay, but it's really important to understand what's going on there in a Pore scale perspective, because then you can try to upscale this behavior in a larger volume. Okay. Then I will start here with two really great case studies regarding, I think, all the scales, all the possibilities that you can perform using the digital rock technologies. And this one here is a fresh paper. It's from the beginning of this year. People from England and Kuwait oil company, they perform this kind of evaluation. It's a digital workflow. So we will start with the acquisition of the whole core. You're going to see this, and you're going to do like a multi-resolution and advanced computation using Let's Boltzmann in this case. You're going to use some conventional techniques to give us some hints, some ideas, or at least to do like a quality control of our results. Here I put in this bullet here that permeability and porosity data could be scaled by the whole core. Yeah, as I mentioned, we started the simulations in the smaller samples, understanding and the physics behind the problem. Yeah, try to correlate this with the larger volume, and then move on to an upscaling perspective. When we do this kind of acquisition here, the whole core, for example, we can do this using different energies. If you remember the talk we had yesterday, we discussed about the possibility to enhance the energy. And then we have two different results when we do the acquisition, the micro-CT acquisition. If you combine both of them, you can take some interesting results of this approach. I'm going to show you in the next slides. And then we can compute this kind of anisotropy between the vertical permeabilities, and you try to correlate the anisotropy ratio. And in the final of this paper, they discuss the possibility to use this for high complex reservoirs. Yeah? And here in Brazil, you can use this for a pre-salt region that you have this kind of highly complex carbonate rock reservoirs. So just to start, you can see here that we have a whole core, yeah? Some low density and high density textures identified. Take a look at the photo, at the core itself. 4 feet here, there are presence of fractures here. It's interesting. In this digital perspective, there's no problem if you are dealing with a fracture system, for example, like this. We can use some digital techniques. I'm going to show you later. Try to fix these fractures there, to try to come back to the original core aspects. Okay, so this moving here, this is the complete workflow that was used in this specific study. They started in the red star there. You can see here. So we start with the dual energy CT scanning that I mentioned before. So we have the whole core. We're going to scan the whole core in a CT scanning. You're using 2 different energy to get 2 different results. And combine them, you can get some information. Yeah, I'm going to show you as well. Then you can select the location of your plugs to be extracted. So it's really interesting because you can perform this kind of digital plugging. Yeah. So you can select a region that you see there is no fracture, there is no, it's not so heterogeneous, because then you can select this sample for a SCAL procedure, SCAL measurements that you can perform to correlate with some of your own results, digital results. So it's also part of the digital rock technique to perform this plug-in selection in a digital way, okay? It's a digital selection. And then you can discuss with the geologists, with your team, and see it's okay. And then you can plug in the real core. Yeah? Here's just a digital plugin. So we can perform a high resolution, in this case 40 micron voxel. It's enough to get an overview of your sample, of your plug. Yeah. Once you extract this plug, you can perform this 40 micron voxel acquisition. And then you can select some, what we call wafers, that are some specific here that you can use to perform, for example, MICP experiments, or at least to cut a small sample to perform the thin section analysis, perform, for example, SCM, EDS. It's possible to perform different conventional analysis that is here based on selection of the wafer from the previous. So you just need to cut a small part of your plug, or if necessary, of course, you have to cut inside your plug, but this is the main idea. You can select some regions to perform this conventional analysis. Then we move to the higher resolution acquisition and imaging, and we're going to perform several numerical analysis, inlet Boltzmann evaluation, and then integrate this information with the information from the lab that we have here. We can perform this kind of evaluation to upscale for the whole core. Okay, so we're going to use this kind of multi-scale, multi-resolution approach. We're going to use some kind of trends to correlate the K-phi behavior, and then based on these properties, try to scale for the whole core, the whole section. This is the complete workflow, ranging the digital rock approach. Let me show you. Let's take a look at some of these the specific steps here. The first one, as I mentioned, you have the whole core here. You perform the dual scanning acquisition. Yeah. It's a CT scanning, so it's like, let's say, 500 micron size. It's not like a usual higher resolution acquisition. And then, based on these images here, we can discuss, we can take a look at the results, selecting, for example, these two regions here. We know for low density, what we call, and with a high density. It's clear to take a look at the CT data and differentiate both. Okay? And based on it, you can select the plugs, perform this kind of higher resolution acquisition. So here we have the 40 micron, moving for a 4 micron per voxel. It's here. So it's a small volume here. And then from this one here, we are moving forward to a higher nano CT acquisition with 65, with 0.065 micron per voxel. It's a really high resolution, and we can perform the numerical analysis of these scales. Okay, even in the larger scale, of course, we have to get information from this smaller cores here, and kind of correlation. We have to consider the real physics behind the simulation, and as I mentioned, kind of non-scaling to perform the upscaling. Based on these results with the lab conventional experiments, we can link all of them to get some hints, some ideas what we can find there in our Pore system, in our sample, for example, and then you can upscale again to the whole core. As I mentioned, using this information in even smaller scales to get the right simulation, the right pattern. Then you have to perform these simulations in all scales, correlating them with lab results, and then correlate to the whole core. Okay, so that's one of the possible approaches using upscaling. We have to do this kind of multi-resolution, multi-scale, trend correlation, and then based on these results, we can perform the upscale for the whole core. Okay. Here, one of the results, we have these selected cores here. We can perform this dual energy CT, as I mentioned before. Based on the CT scanning, with some processing, some numerical analysis as well, we can correlate this level from the CT with the density of the book, and also with the effective atomic number. It's a solution that can be provided for the whole core here based on the CT, dual CT scanning, when you can create this kind of log profile here based on OB, for example, the density, and the atomic number. This is calibrated using a from membrane, and then you can correlate with well-known specified materials, and you can have this kind of log here. Okay, you can perform this for the core, and you're going to show later. You can perform this for several cores and try and do this kind of stitching procedure to get the full, the complete analysis of your core. Okay, this is one possible application from the beginning of the CT scanning acquisition. Okay, do some kind of post-processing, understanding of the CT values here, the grayscale values here, and you can perform this kind of reconstruction of the log profiles. Here's just to give you an overview again. It's a plugin, a digital plugin. We selected the plugin here inside the core. Just before we cut this, look at the heterogeneity of the sample, if there are some kind of fractures or not in the sample, and then if it's okay, we can perform the real plugin. We can go to the core and then select the region and extract the plug that we are interested in. Here's just an overview again with the density here based on the length of the plug, and we perform this here in a digital way again based on the plugs that we selected using what we call in grain the plug 8D. That's the analysis of the whole plug, but using not using a higher resolution. To give an overview how are the distribution of density around your sample, because sometimes you have this kind of heterogeneity, local heterogeneity, and you can see this kind of peaks in this first year. So it's just a second step there. You can evaluate. You can perform this in a digital way, and then using this what I call the plug 8D, the analysis of the plug with 500 micron per voxel. You can look at the regions of high density material, regions of low density material, some kind of higher pore system, heat pore system here, for example. It's possible just to take an overview based on a low resolution acquisition. So if you do not like this sample, for example, if you're not interested to perform some kind of SCAL measurements in this one, you can just consider this and move it to a different section of your core and select in the digital way again your sample. And then we can move forward to the real extraction of the plug, and then we perform a higher resolution acquisition here with 40 micron per voxel. And with this acquisition, we can take a look at some regions. If you have too much high density material in one region, you can avoid this region, or you can select a different region to perform the higher resolution simulations that we want to do. Yeah? So this kind of downscaling in a way that we are reducing. We are working with smaller samples, but you are considering that they are capturing the flow system we have in our previous larger sample. Okay, it's really important because when we select this high resolution subvolume there, we can perform, of course. Meanwhile, you are performing some traditional experiments here, for example, thin section analysis, to take a look at what kind of pores you have, what kind of minerals, what kind of connection between them, and MICP, of course. You want to perform this, as I mentioned before, you can use like a wafer of your original sample, of your original plug, in this case, and you can perform this kind of frozen distribution and see the peak of distribution. In this case here, we have a peak of around 0.1 micron. Yeah? So you're going to move to higher resolution this information. Selecting, for example, 4 micron per voxel, 1 micron per voxel, 500 nano per voxel, just to capture the majority parts of the distribution here in the smaller range. Okay, it's important. The MICP is one of the steps that you can perform to do like quantity control for both the pore size distribution and also the capillary fraction, the capillary pressure as well. Yeah. So here, for example, once you have this selection of the plug, you can perform in a wafer, as I mentioned before, the selection of different regions based on the previous analysis of your CT images, and then you can perform you can cut your sample in different volumes and perform the high resolution acquisition in each one of them. Okay, if you identified in your previous wafer some different regions, some different characteristics, select several samples to perform this kind of high resolution analysis. In this case, they performed the 4 micron per voxel, and then move on to 6.5 nano per voxel. Increasing the resolution, you are more smaller pores, smaller pore flows radius there, and then we can perform it, as I mentioned before, let's do simulation in all of these scales. Okay, in all these scales, we try to think that we can capture some information of this higher resolution to provide some necessary information to the other scale, to a low resolution scale, let's say, and then you can reconstruct a good model that you are considering several scales information, and they are enhancing your results. Okay, it's really important. That's why I mentioned about the multi-scale, multi-resolution. Okay, and performing this kind of evaluation, we can correlate with some kind of data. Yeah, as I mentioned before, you can try to correlate them, create this kind of trends between scales. It helps you to identify some characteristics of your persistence of your sample. So we are moving in this direction. Yeah? We did this multi-scale approach. We did this kind of trends analysis as well for each one of these smaller volumes. So just like you can perform several simulations from these smaller volumes, and then plot this kind of trends respecting the size of the sample that you have for this specific voxel size and the specific resolution, and then you can do the same evaluation in the next resolution. Okay, it's like an analysis with trends. And one of the things that can be done using digital work approach, for example, here we have this kind of fracture sample. Yeah? One of the possibilities is try to, what they call in the paper, to heal the fracture. Yeah? So you try to understand the main features here in our sample in a 2D section, for example, and we try to reconstruct the original sample without the fractures. It can be done in the 2D sections and then modeling for the 3D distribution as well. It's possible to perform this using machine learning based techniques that can perform it based on the original sample that you have. So as you can see here, we can perform this for the whole core, yeah, the whole section here. And then, based on this information, we can correlate with the trends some information for porosity, and based on some simulations, some other information about solid permeability in different levels. And for porosity, it was calculated based on this situation here. When you have the porosity of one volume fraction here and the porosity of the second volume fraction, you do this kind of correlation between them. But for the scale of permeability, perform several numerical analysis, numerical simulations in several scales, and then combine all of them. And for this case, it used the Darcy simulator to perform this in larger volumes. And then, with this kind of results and information, you can do this kind of correlation to the whole core. Okay. Again, here it's just some of the results that was stated in the table here, but plotted in a trend graph here. This to make sure that we are trying to capture if there is some kind of trend, if we are capturing this trend. Yeah. So in blue here, there's some digital results. Yellow and green, you can see that we perform this for the pure low density, high density plugs to create this kind of maximum and low, minimum values. And so we have some kind of measurements from the plugs from high and low dense materials. So you can see here in red low materials, in blue high dense materials, and then we can plot this correlation between them like a trend. We can perform this for the vertical or horizontal permeabilities, and also between horizontal permeabilities results, try to correlate both of them as well. So it's all parts of the analysis. We could simulate in several smaller samples using this information to populate the previous low resolution sample. And then once you have this information, you can plot the results. You try to correlate the real plugs and the information that you have from the whole core, for example. And then if you find some kind of trend, you can use this trend to perform a evaluation for the whole core. And then here to show you, it's some results of the permeability, vertical and horizontal permeability versus porosity for the whole core. That you in this case, if you have this kind of fracture or some regions that are not well identified, you can perform this kind of machine learning technique. You can perform all the workflow, and you can plot and take a look if the results are okay or not with your real data. So here, in the digital perspective, we can work with the fractured samples, whole cores. If you have some kind of plugs, if you have some cores that have been already plugged, you also can work with them. Okay, it's a really interesting possibility. I would like to address this in this here of the case studies is one from 2017 as well, from the Ingram and Kuwait Oil Company again. Again, they are working for a robust sampling strategy using dual energy CT scanning, 3D reconstruction. But in this case here, I'm going to show you some of the SCAL results as well in the pore scale perspective, because then you can understand what's happening, and we can try to correlate this for the whole core again. As I mentioned, they could provide this kind of information results in a relatively short time frame if you compare this to the real lab experiments. So here, one of the first results that they got from the acquisition, we performed the OCT energy acquisition. It got information about the, as I mentioned before, the density, the pore density. So here we are plotting the density. You can see here that according to each CT grayscale value that you have, you can correlate for a different mineralogy. So it's what I'm going to show you here. Between the steps here, you can perform some kind of digital analysis as well, some kind of machine learning based segmentation to perform this cutoff by the main mineralogy of each of these SCAL phase here, okay? And this is a result from the dual CT energy acquisition, okay? It's a relatively quick results that can be provided based on this CT scanning. Then once you recreate this kind of density effectively, you can correlate them with your own core. Okay, I'm going to show you here that they can be, you are working in different scales. Here we are considering in this example almost 450 feet of sample, so almost 112 meters. But then this is here what you are seeing. This all the data that was captured. If you do like a zoom in specific regions here, you can see the profile that was generating using the digital approach. And then you can, for example, identify that you have more sites in this core here, for example, this first one here, and the second one, that's changing between the formation to the other one here. And for example, in the last one, you have this kind of sandstone here. And on this color scales here are also generated based on the capability of this dual CT energy analysis, okay, for the whole core. And then if you go for the, in this case here, we started with 450 feet and go to 50 feet here. It's almost 12 meters, something like this, 12 meters almost, but we can go further to the whole core scale here. As you can see, it's around 1 meter, this one here. As I mentioned before, we can work even if you have this kind of core is already plugged, if you have this kind of fractures, if you're losing some material, you can consider this, of course. Some of these regions here, you don't have complete information, but can help you a lot to identify at least some regions here that it's interesting. And here, just to show you that you can start with a larger, you can start with this small acquisition here in a whole core scale, and you can put all of the data together to generate the full log here that you see in the first slide. It's an application that's the workflow is similar to the previous one that I showed, okay? And again, once you identify these regions, what is described here as RT1s, like in a rock type 1. But once you identify these specific regions here, you can try to correlate them, use this kind of trends again. Yeah, if you have a good correlation, as this one here, that's a common example. So in the other parts here, they identify 3 different regions as well with a trend. You can see that there's no good correlation, but they're going to try to use them as a first step procedure, to identify a possible trend if there is one, yeah. And again, we start with dual CT energy scanning. We're moving forward to analysis of some kind of trend between the permeability porosity for the whole core. And then based on the selection of the plugs that can be done previously in a digital way, and then in the selection of the plug, yeah, we can understand some patterns that we find in the plugs, the distribution of the pore flow radius, yeah, and generation of the PC curves as well, as you can see here, and some thin section analysis. This kind of conventional or at least laboratory experiments that we can perform, are going to help us a lot during the evaluation and the correlation in the several scales in order to be able to procedure to go forward with the procedure of the upscaling. Okay. Here again, just to show you some of the distributions, and of course you can identify in this case here from the high dissolution to a high cementation, high compactation here. You can find here that you are decreasing the pore flow radius. Yeah, there's a peak here around 2 or 3, and then removing until 0.03, 0.04. So we are decreasing the permeability and porosity in this case. Here for the other region, and when you have that clean sandstone here with a very clean peak around 10 micron, but then if you are moving in these regions of yellow sandstone and siltstone, you can see that there is kind of model distribution or with low values of flow radius. Okay, so it's a really important step as well, this evaluation. And then, based on all the integration that we performed before with the dual CT energy and some information from the plugs, pore parent plugs, for example, we can generate these profiles here that we are going to see. Of course, this image here is not so sharp, but I want to show you in the next slide one of them that we can discuss a little bit more. So, for example, in this one here, we are comparing the one log OB with correctly this CT, okay, that we're generating using the dual CT scanning procedure. As you can see, both of them match. Yeah. Some regions here, we have this kind of not well correlation. Even in this region here, you can see that in the caliper, you have this kind of information. Yeah. So it was really important to do this kind of correlation here with like a real measurement. Yeah, we could provide the CT correct intensity, CT effectivity number, the CT porosity correlated with the porosity, and the wireline porosity, as you can see here. All of them are matching in a good way, except of course in this that we just discussed. And also for the permeability, we could correlate to what we predict from the trend that I showed before with some plugs perform the pore measurements. So to give you a zoom in, but in a different here. But it's possible to generate this from a digital rock perspective. We can correlate for some trends here in a larger volume, and of course honoring the values of the plug. Yeah, it's really important. So it's also part of the. It's also a digital rock procedure that can be done using micro CT images, yeah, and some post-processing evaluation and correlation. Okay. Here again is the image that we just saw before, and the reconstruction of the cumulative MICP, and using 2 different resolutions to capture the main features in each one of the scales. Okay. Again, we can perform this kind of correlation with the capillary pressure curve using the information that we got from the simulation in smaller scales. And then there are some kind of upscaling procedures using simple equations here, just to take a look and to see if the values match. Okay, it will be interesting because you can do this kind of simulations, PC curve simulations in several scales. But then when you have to provide this for a larger scale, you have to generate some kind of correlation between them. Okay, it's just a quick review of this. Here, as a result, in the carbonate selected sample, from this selected here, we could take a look at the results in the sync section analysis from the higher resolutions. As you can see here, a cube that we selected, and we perform the plug and the microsample process analysis in a way that you can try to correlate both of them during the sample length. And if you have this kind of correlation, not only in porosity sample correlation, also with the saturation and pressure, you have to match both of them, or at least well what we saw in the lab experiment, and what we generate using the digital rock approach. And just a matter of comparison, yesterday I remember we discussed a little bit about it. Just some results here. For example, the porosity in the plug for the carbonate rod, we found 20% porosity, and then when we performed this in the lab experiment, we found 22.4 for the microsample. When as I mentioned, capturing the features from the higher scale, from the higher acquisition, and in different scales, we got 26. And then for the scale data, using the correlations from the micro scale, performing the downscaling to upscale procedure, we found 21%. So you can see that's a really good match between them, and the permeability is the same, ranging between 3.22 until 3.56. As you can see, really good match here as well. The same thing was performed for the sandstone samples as well. You can see that we have, of course, a higher permeability value, but we could at least found the same order of magnitudes that we found in the plug, or in the MICP in this case. And again, I have pondered the distribution of porosity and the pressure curve that we got from the lab, and we generate from the digital numerical analysis. And just to show you that it's possible to perform this, the generation of the capillary pressure and relative permeability curves based on the numerical analysis. Of course, you can compare with the lab experiments, but you can perform several sensitivity analysis, changing mutability, capturing, in this case, for example, the reducible water saturation and the residual oil saturation as well. So here, just to show you some generated numerical curves from the primary drainage and inhibition, in this case, in a carbonate sample. Okay, we started with a water wet scenario and move on to inhibition in a water wet scenario. So you can see this kind of mirror image that was painted in the literature, and we could see kind of hysteresis between the curves as well. Here, in the Pore scale perspective, we could honor what we saw in the physics behind the problem. We could perform the primary drainage, and then in black here you see water, and then oil is in the water, and some regions here you keep the water, and we got the reducible water saturation. Then we perform in a oil wet scenario the water displacing the oil, as you can see, water in black here, until we reach the residual water saturation in the final of the numerical experiments. So this one in the Pore scale perspective, this kind of information we can incorporate in several scales until we reach the scale. Here is for the sandstone sample, just to give you a quick overview as well, that you can perform the same experiment, numerical experiments. And I just compare some of these curves here, but then changed it for a water wet scenario in this case. We performed the water wet scenario for the primary drainage, and for the inhibition, we repeated, but keeping the contact angle lower than 90 degrees. And then you can see this change of the curves, the pattern of the curves. It was done also in this study to take a look at what's going on in the Pore scale perspective. So here, just to give you a really quick overview, we could find this kind of snap-off displacement phenomena here, and then we could compare with the previous scenario. So it's one of the things that Let's Bolt method can capture. And of course, you can identify the layer of the thin layer of the fluid that is in your system, you can try to change this kind of contact angle, the values of IFT as well. So yeah, you can identify or at least study several different scenarios and correlate them with your own data. Yeah? Here again, just to show you some of the last results that they could compare water wet and oil wet scenarios for inhibition in this case. And it was part of the development during the workflow that they selected to confirm that they were working in the right direction, they were performing the right simulations. Okay, so it was interesting because we started with the larger, with a whole core. Yeah, you perform this evaluation until you reach a higher resolution 3D model, 3D based model. You can perform several simulations or several post-processing analysis there. Then you can move on again to larger scales, incorporate this information, the trends that you can generate from the relation between the several parameters. And this is a possible approach to fulfill, to perform all the workflow, to work from the pore scale to the core scale, okay? It's a little bit from my time, but it's a lot of information, a lot of case studies. Just as a short review, we can incorporate several aspects of the physics behind the two-phase flow simulations. We can do a multi-scale analysis there. Yeah? We can perform in the whole core scale some really interesting analysis to generate some logs and to compare with the real data, because then we are dealing with a higher resolution image. Yeah? If you compare with the analysis of the whole core and the wireline whole core, and with our digital perspective. And honoring all the physics that we discussed, you can simulate, you can do this kind of post-processing, and that's why I think digital rocket technology can help you a lot to understand your fluid flow system, how the fluid flow is, how the fluid is flowing in your system, how the pore, how the interaction between the fluid and the rock in a pore scale perspective, and in a way that if you have enough information about this correlation, you can go further for a new frontier that's the whole core analysis. Okay, I'd like to thank you. I passed a little bit of the time, but as I mentioned, too much information.
Thank you, Leon, for the nice presentation. So it's time open for questions, even though the voice wasn't that clear most of the time, unfortunately. So anybody has a question, you may go ahead and ask him.
Feel free to contact me by email if you want. For a reference, that I have all the reference there, I can send you the links. And if you have any question about the workflow for ingrained workflow, how to work with the whole core and the pore scale perspective as well, you can also have my email from Halliburton. Okay, please send me an email. I will answer as soon as possible.
So did you send me this lecture, like this lecture slides?
Yes, I will send you for sure.
Okay, because I received yesterday lectures earlier, but this one is new.
Yeah, I have to cut a lot of the slides because too much information. I have to keep it inside the time frame that you have. Huh? But I want to send you this last version.
Okay, thank you.
And feel free to send the PDF. All the reference are here in the presentation. Okay, if there is some other reference that is not well defined there, I can send you later. Just contact me.
Dr. Goddy?
Yes.
Just I want to ask you about the permeability that we get from the core. Is it always horizontal or sometimes be vertical?
The permeability.
The permeability we get from the core.
We can calculate it in the vertical and horizontal. We can also generate some correlation between these two permeabilities in order to have this kind of anisotropy ratio. It is possible, yes.
Okay.
Yesterday lecture was also, the voice was also bad, but the records was good. When we posted the lecture in YouTube, I checked it, it was good.
Okay, thank you.
We'll have the same thing today.
Yeah, probably is some problem with the connection, because I think people here in Brazil, they can listen me clear. I think they reply me that it was clear to listen, but I don't know. Probably you have some, we have some problems with the data transfer, yeah?
Yeah.
The previous question, yes, we could generate the permeability vertical horizontal ways, and then we can also plot them together, yeah? Trying to find some kind of trends between them, yeah? It is also possible.
Mm-hmm.
Please feel free to contact me if you have any questions regarding this part. I can forward to our consultants, to the experts in each field of this here, because as you saw, there are a lot of information, a lot of different field of studies here. And of course, if I don't know exactly the answer, I will ask the consultants, our friends here, okay?
Okay, sir.
So if no more answers, if no more questions, we can like end the meeting now. Any more questions? Okay, so we need to end the meeting for today's lecture. So on behalf of SBE Basra section and Adaptive Geoenergy Research Center, we thank Dr. William Goddy for his informative lectures. And we hope to get like future opportunities for different topics. Thank you very much, Dr. William.
Thank you very much for the invitation, for your time. As I mentioned, a lot of information, but if you have specific questions, please let me know. There are my contacts here. And again, thank you very much for this opportunity.
Thank you.